Okay, so we'll start by installing Vivado. Um, so first, this is a version that is really common, the 2020.1. We use that in our classes right now, but it doesn't really matter what version you install, unless you're concerned about some depreciated functions that you may want to use. Um, but um, Actually, let me demo this. So, can you see my screen still? Okay.
Yes, go ahead.
Uh, so just Google Vivado downloads. Go to this page. Um, there should be a installer that you can download. Click on that and fill out your information, and then you can download um, Vivado. After you've downloaded it, just install it, and this is what it that will look like. Let's go back to the PDF or there. After you're done with that, um, oh yeah, we already went through this part. Um, After you're done with that, you'll see this page where you can fill out your username and password. That's the same username and password that you created when you fill out your info previously. And then we're going to accept license agreements. We're going to select Vivado, which should open in a bit for us. And then after that, we're going to select the Webpack. This may be updated a little bit in the latest versions, um, but yeah. And then we'll select the design suite. You may want the software development kit if you want to code in other languages like C, C++, or um, MATLAB even. So let's walk through this. Um, yeah, so just type your email address, your password, and then it'll take you to the screen. Just gonna cancel that now. Uh, yeah, just select these options and you gotta wait for a little bit. This is the older version, so the disk space required here is 21 gigs, but for our version 2025.2, it'll probably be around 60 gigs. So yeah, it's a big program. So we're gonna have to be a bit mindful about the space. Um, yeah. So let me open Vivado. Um, let me stop that. So after you install the software, um, you can just go to project and then new. Next, just create a program, name it anything. Um, so you can name it and three. And this has to be a RTL project. If you want to import something or if you are using IP cores, then you can select any other option. But if you want to code NVHDL or Verilog, it's going to have to be RTL project. and then select a board. This can be found in the datasheet for your specific FPGA board. Uh, and this is the configuration of the board that I'm using. Um, all right. All right. Now, the first thing we'll do is create a design source. There are three uh, things that we can create to uh, define functions and stuff in VHDL or Vivado. Um, and one of them is the design source, the other the simulation source, and the other the constraints. The design source basically has the logic for your circuit. The simulation has the code for your timing diagram if you want one. And the constraints basically connect the uh, ports in your design source to the ports in your board. So you're basically mapping the things to your board with the constraints. So let's create a design source first. Let's create a file. So the language is Verilog and name it something. And 3 and finish that. And now we're going to define some inputs and outputs. So for this one, let's just create a basic AND gate. Um, so A and B, those are our input. X, that's our output. Just click OK, and it'll generate a design file for you. Just go there. And that this is generated for you. You don't really have to do much on this. But now here is where we put our code. And that's just it, right? That's just it for a AND gate. Now, now that our logic is complete, let's add a simulation source. Let's create a file. And it's better to name this the same thing as the design source, but with a test bench extension. So just like that, and 3 underscore test bench, and just create that. And yeah, we don't have to really define anything on there. Okay, and then we set this guy as top. So what that means is we're basically saying which file to read first in each of these scenarios. In the design source part of the code, the design source needs to be the top, right? Because that's where the logic comes from. And in the test bench, the test bench has to be set as the top. But there may be scenarios where you will use different modules, which we'll go over in a few minutes. That is where you will basically have uh, multiple modules in the design source, and then you'll have, at that point, you'll need to have your top module set as top. Essentially, the module that is calling everything else, that has to be set as top, otherwise your code won't work because Vivado reads the code that is not the top first, and that causes issues. Yeah, so let's code the test bench. Now, here, what we're gonna do is we're gonna take this and import it as a component, put it right after the architecture, change that to component, and then we declare some signals. And then we create a port map. So what a port map is go back to this guy. So what a port map is basically this guy. So what that does is it connects the inputs and outputs from our design source, which is this guy, the A, B, and X, to the inputs and outputs um, in our simulation file. So how we'll do that is just paste that over here. And yeah, I gotta rename this to and re. Also, these files, they are not case sensitive, so at least the design source and the simulation source, they are not case sensitive, um, but the constraints are. So you'll have to keep that in mind when you code. And after that, we'll just create a process block where we'll define values for these things. So what we've done with the port map here is basically this is just name. We're just naming the port map. And then we're defining what we're creating the port map for. Uh, and then just port map, and then we're connecting the ports, these things, to these signals that we have created. Now what we're going to do is just make um, like assign values to um, these guys. Um, so maybe something like that, right? Um, and we may need to add a or 10 seconds. All right. Now we're gonna copy that part, and it's okay. Like this is just to see if your circuit is working, and like with a timing diagram, but you don't really have to do this part. Um, but yeah, it doesn't matter how many test cases you put in. We can only have 4 test cases because we only have 2 inputs. Um, all right. Now we'll save that and still something going on. Mm. So
Any problems, Raman?
no, no. It's just some syntax error that I'm
Mhm.
figuring out. Um, Let me just copy that part, the entire process block from here. Okay. Yeah, there seems to be some issue, but yeah, it's fine. Now, after we're done with that, we're gonna run the synthesis. So there are three things that we need to let the program complete on its own to make like these things run. Um, so we can do the RTL analysis, but that is not really required. What we need though is to run the synthesis. So what that does is it basically takes this code and the simulation file, and it synthesizes a block diagram with the circuits. Um, and then that will let us run the simulation, which is the timing diagram, which we'll see in a bit. Now, we can see the progress in this synthesis over here or at the top right of the screen. We're just going to wait for that to complete. And this does take time, so especially with big projects, it does take a fair amount of time. Um, so yeah, this is just a time where you have to wait and can't really change anything in the code. Otherwise, you're gonna have to run the synthesis again. Um, but yeah, okay. So our synthesis is complete. Now we're just gonna cancel that part. We're just gonna see the behavioral simulation. All right, I'm gonna press on that. Now, what that is doing is it's basically showing the behavior of our circuit to us. A and B, those are our inputs. So we've given we've given the values of A and B in the test bench file. So A is 0011, B is 0101, and the high is 1, the low is 0. So 0011, 0101 is exactly what we have, and this is an AND gate that we have created. Um, in an AND gate, it's the output is only true if both of the inputs are true, which is exactly what we see. So this is our AND gate, and it is working according to the timing diagram. So this is one of the ways you can verify that your logic is working. And this is just a simple uh, way that you can do this, but of course there is the board that you can implement your code in. And now for that, what we're gonna have to do is create constraints. So it's either this, just create constraints from here, or what you can do is run the implemented design, wait for a bit, and it's running right here. And what you can do, what the implementation does is it basically is mapping out the device for you. So you've provided it with what device you're using, and it has all the um, it has the maps of all your components in the device, and I'll show that to you in a bit. Uh, but it is basically mapping the code to your board when you run the implementation design. And here, let me just show you um, something that may be a bit more helpful when you're testing your circuit. So when you open the synthesize design, it'll show you a circuit. Uh, yes. So it'll show you a circuit of your logic, and these are our inputs, A and B, and that's the where our code is being processed, right? That's the lookup table where you can see uh, if you see the truth table, this is the AND gate truth table, right? So this is one of the ways you can verify your results. And let's close that. Go back to, okay, it is going to take a bit. And yeah, this is this is one of the places that takes the most time in um, just running the circuit, because it's just the software doing its work. We can't really do anything about that. So yeah, let's open the implemented design for now. Um, so this is what your device looks like, or what the device I've chosen looks like. Um, so there are a lot of components here. As you can see, some of these are pins, some of these are LUTs, some of these are flip-flops, and it's sectionalized. And you can go through it through this if you want to, but for the general stuff, you don't really need to. But if you're making IP cores or more complicated circuits, you may need to go through these. But why we are here today is just to go to the I/O ports and then define what pins we're going to be using. So in your FPGA board, there should be numbers um, in your like near your LEDs, or you actually can't see that, but if you can see the switches and the LEDs above them, they have numbers in there that are printed. And what we can do is just assign the switches to the numbers in the board. So the inputs are going to be the switches, and the outputs, so L16. This is on the board, or you can go to a data sheet and find this as well. If you're using a breakout board or something in your FPGA, um, you may want to confirm with the manufacturer what your uh, FMC, whatever you're connecting the breakout board with. You may want to confirm with them how you're going to connect, make the constraints pretty much. Um, and also we have an IO standard. Um, this is basically how much voltage the inputs and outputs require. So we're just gonna do that and just save it. Save that and name it something. All right. And as you can see, after that, our implementation and synthesis, they're out of date because we have changed something. It just says that above, right there. But we don't have to run all of these things again. We're just gonna run this bit stream, and it basically runs everything for us. Um, so yeah, we're just gonna wait on that. And actually, while we're waiting on that, I'll go through a um, I'll go through a little more advanced topic in FPGAs. Um, okay, that's going to be running on the background. And if you can see this PDF, which I think you can, let me just make sure anyway. Um, okay, all right, all right. So this is one of our lab guides, and
Please
this is one.
make it slightly smaller because it's overseen. Yeah.
Okay,
Okay, it's fine now. Right. Go ahead. No,
all
no,
right,
it's could be a slightly bigger. Right. Right.
okay,
Okay. Thanks.
all right. So this is one of the uh, basic concepts that we have in our class where we use different modules to basically outsource the work, um, so that you don't have to define everything in one module, which actually helps a lot with complicated programming. Um, Now, how we're gonna do that is it's kind of the same as how we did the simulation code. We're basically going to import the design source as a component, and we're going to make port maps. That's basically it. But if we want to connect two different modules, we're going to have to use signals. That's pretty much the gist of it, but I'll walk through this presentation anyway so that it's a bit more clear. So here we're creating a half adder, a full adder, maybe not a ripple carry adder, because we don't have much time. Um, but yeah, the
Uh,
picture will appear
Actually,
anyway.
Raman, we have time. We have time. So
Okay,
please don't shortcut things.
okay, sure. Um, all right. So let's start with the half adder. This is gonna be a simple code. Uh, if you notice in binary addition, we have like binary addition of two single input numbers. We can have a sum and a carry, where if the inputs are one and one, the output is the carry is one and the sum is zero, right? It's 1 0. 1 plus 1 is 2, which is 1 0, right? So that's basically what we're trying to illustrate with a half adder. Um, it's just basic stuff, but I want you to look at this part. So the sum, we're gonna make simulate that with the XOR gate, which gives us 0 1 1 0, which is basically what the sum would be when you add these numbers in binary, right? But the carry is only one when both A and B are one. So carry and sum, that makes it 1 0, which is 1 plus 1 is 2, which is pretty basic. Um, but yeah, we used XOR gate and an AND gate to make a half adder, which basically illustrates us adding two single bit numbers together. But now, and that's the simulation code. We can sim It's basically the same thing what we did previously. Um, but let's move on to full adder. Now, with the full adder, what's happening is we're adding another bit, right? We're adding another bit. We are adding a carry in bit, and there's a carry out bit. We're just differentiating between the two carries. But the outputs are pretty much the same as before, the sum and the carry. But in the inputs, we're adding a carry bit, which is, yeah, just adding another input. So in this guy, what the maximum output would be is 1 plus 1 plus 1, which is 3, which is 1 and 1. The sum and the carry, both of them are 1. So we could use a gate. We could use a number of gates to do that, but how we did it in this one is we used two half adders to make a full adder. And let me show you a logic diagram to make this more clear. Should be okay. Here it is. So how we did that is we put a half adder in here. The output from the XOR gate of the first half adder is a input in the other half adder. We added another input, which is C in. That is an input in another half adder, in the second half adder, and the carry from both of them goes to OR gate, and then we get a C out or a carry bit output, right? So how this would work in um, oh, okay. How this would work with a truth table is basically um, we will have three inputs, A, B, and C in, and when only one of them is on, the sum is one, but the carry is zero. When two of them are on, the carry is one, but the sum is zero. Pretty much the same as before. But the last part that we added, where we also include the C in um, right here or right here. What that did is it included an extra bit. So we'll get a one in the carry bit and one in the sum bit as well. If that doesn't make sense, please be sure to ask some questions. And what else? Yeah, let's move on to how we actually do this. So this pretty much uh, looks like a code that we did previously, right? Um, and it is true, but on the top module, what we do is import them as components first. And then we make a port map where we basically connect these things, the inputs in the top module to the inputs in the components that we made here. And we connect the outputs as well. And that gives us basically a architecture to basically connect these together. We don't have to really make a OR gate and AND gate over here because we're importing it from these logic design sources. And yeah, that's basically it. Now let's go back to Vivado and see if our code is done. Okay, so as you can see, both our synthesis and implementation, they are done, and our bit stream is complete. I'll just cancel that. Now we're gonna open the hardware manager. So the FPGA is connected, and what we're gonna do is we're gonna open the target, auto connect. It connects with a local host. So you're gonna have to allow network access to Vivado. And if you have antivirus that may interfere with it, or if you're running other software that uses localhost like PuTTY or Apache, anything that may interfere with it. So please close that before you run this. Now we're just going to program the device, and that's just the file that we created with the bitstream. And let's program that. Now what I did was I set these two pins as A and B, and the LED over here as the output. So when one of them is on, nothing happens. Right? When one of them are not on, nothing happens. When both of them are on, it lights up. So that is our AND gate, right? Now, let's show, let's move on to what I just explained um, with lab 2. Um, okay. So this is the full adder that I was talking about. So how that will look after you do your port maps and you um, import the uh, modules is you'll have the full adder, which is the top module set as top. And if you don't, you're gonna have to do it. Otherwise, it'll cause errors, and you'll have half adders as components, right? Um, okay. Hold on, just give me a minute. It's just all right. Now we're just gonna create the constraints, or we can just run the synthesis. So this is our half adder, which has pretty much the same logic that we saw a few minutes ago. And in our full adder, we've just imported it as a component. We've created a few signals to connect these components. And then we've created port maps for the two half adders that we're going to be using. Um, Now I'll just wait a bit for that guy to complete. I'll wait for another presentation file. Okay, let's run the implementation as well.
Yes, Raman. So could you maybe mention something about your the Galton board experiment?
Yes, yeah, I'll
But
go through
just
that.
first finish what you have still to be said.
Yes, I'll go to it right after this. This is kind of essential for that. So I'll just go through it, this first and then the golden word after. Let's just let this run. So the basic concept here that we have to understand is we can import other modules to another module to just outsource the work, pretty much. So yeah, that's pretty much the basic gist of it. Also, of course, we have to use the signals if you want to get the information from one module to another that are not immediately connected. So to get the information from the half adder to the first half adder to the full adder, we don't really need signals, but we're taking the information from here to another half adder where we will need signals. Um, yeah, so that's basically the reason why that is happening. But uh, just let this run up for a little bit.
after this lecture, can you send me some materials so I can distribute in relation to your course so our students
Yes.
can benefit? Right. I think it's also good advertisement for your business skills in a way because you are building a market right now of possible clients, right?
Uh, maybe. So here we'll just go to the I/O ports. Um, Now we're gonna define these um, pins exactly the way that we did before. So the inputs, they have to be pins. This is A, so it's the first pin there. And this guy, L16, the second pin. And for the C in, so we'll put the third pin in, 13. Now the outputs, they have to be LEDs. So this guy, it's carry. So let's put K15, the second guy, and H17 here. And the IO standard. Let's just save this. And close that, generate the bit stream. And let's just let that run while we go, uh, while we move on to the Galton board. All right, that is running. Okay.
Whenever you move to a Galton board, give us short introduction what it is as well.
Okay, sure.
You can refer to Wikipedia or any notes you have or any presentations you have. You can also show of your presentation you have shown me last time.
Okay, sure. Um, okay.
In meantime, Eric and David, do you have any questions?
No, I don't have any questions.
Yeah, so I mean, one can introduce artificial algorithms that works very quickly with FPGA actually. So the thing is that the reason to apply FPGA is to omit high software levels and high level of software compilation. So you can get very quick electronics, like when you have a beam in an accelerator, you want to have very quick reaction of after detecting of some anomalies to other equipment to adjust the beam. So in such a case, you don't write traditional program because it's too slow, the input output. So also to trade very quickly on the market, sometimes even in milliseconds or microseconds time, like change of currency values, you can, if there's change of currency values, you can change, make exchange currencies or something like that. So there's a bunch of applications, growing applications for FPGA. So FPGA market is because of that is like, in a sense, replacing standard computer desktop or laptop or supercomputers market to a certain degree. And also at this stage, it's important to mention about Arus supercomputer that was made from FPGAs from which University of Technology from the MCS, Department of Microelectronics and Computer Science. All right, so Raman, go ahead.
All right. Um, I'm gonna share this slideshow. Um, all right. Okay,
Oh,
can you
we
see
see on the
this?
bottom part. Can you somehow shift? I don't know why it's on the bottom. The only part of the slide is seen. The upper part of the slide is seen.
Okay. Um, hmm. Okay.
I don't know, maybe share or reshare. I don't know why is it like that. Sometimes maybe happens.
Hmm.
Any problem, Raman?
Um, it's not presenting for some reason. Um,
In the
okay.
meantime, you can say to us. So, what did you do during your bachelor degree?
During my bachelor's degree, I actually worked with Professor Osinski and Professor Tito Busani on a couple projects. With Professor Osinski, I worked on SNSPDs and signal readout using FPGAs.
Tell us what
Uh,
is SNSP's PSD's
oh,
acronym for.
it's a superconducting nanowire single photon detector. Uh, so it's just a nanowire, which is like super cooled with some superconducting properties. Yeah, and it's actually better than avalanche photodiodes that we're using for this project. It has like low dark count and stuff, but APDs should still be viable for a project. But SNSPDs, the only thing that is kind of um, not great with that one is it needs to be super cooled, and we need something that runs on a board
Well,
for this project.
in a sense, cooled to 4 Kelvin, pretty much. Like,
Yes.
so you,
Mhm.
you you design FPGAs for superconducting single photon detectors.
Uh, to read out the signals, yes. Well, yeah. We were going with that project, but the SNSPDs were not fabricated until the end. And then we just simulated the
You know,
circuits, and yeah, that was our final project.
we can.
Um,
Yeah, yeah. I see. I
mhm.
see. Go
Yeah,
ahead.
Divas is actually still working on that. Um,
Yes, I confirm that he does. Right.
um, okay, so Um, okay. Let's see.
Yeah, go to full screen mode now. Yeah, we see slides,
Yeah,
but
it's not letting me go to full screen mode, unfortunately.
so make it control minus slightly smaller. Control minus.
Yeah.
Eric, is it visible?
Yes, it is visible.
Okay, go ahead, Raman.
Oh,
Okay,
actually,
now
I
it's
can do
even
that.
better. Right,
Yeah.
right.
All right. So, um, all right. So for this project, one of the requirements or one of the things that Dr. Promosky asked me to do with FPGAs is do a 2 to 8 with 2 inputs, 8 outputs, logic implementation on with Galton board on FPGAs, um, and that is basically I've tried to do that with FPGAs, and now here I worked.
Can you,
Uh,
Raman, can you explain what is Galton board? People need to refresh their knowledge. What is a Galton board?
okay, so
Do you
a
have any,
Galton
any
board.
slides or any picture of it? What's the main
On
idea behind Galton board concept and how we can implement Galton board in physical
mhm.
world, also in
Okay.
mathematical world?
So, a Galton board
Do you have a
is
Wikipedia link? Link to Wikipedia, maybe? I don't know.
yes. Yeah, let me just. Mhm. All right. Uh, so a Galton board, basically, if I can see, okay, yeah,
This
there it
might be
is.
five pictures. All right, good, good.
Yes. So a Galton board is basically where you have some inputs over here and whoa.
Inputs like what? Like grains of sand, right? For
Uh-huh.
example, or small balls, right?
Mm-hmm.
And
Grains of yeah, grains of sands or like marbles. And then they strike one of these uh, like dots, uh, which changes the direction of the projectile. And what you can observe at the end is it follows a Gaussian curve. And we have some uh, theorems that do use this principle as well, like the central limit theorem or the law of large numbers, which basically says that with enough randomness, there is a Gaussian curve that forms at the center if there is one input. Uh, but yeah, uh, that's basically what a Galton board is, and how it works. So let's go back to the
in your
FPGA
case,
thing.
there will be two inputs, right?
Yes. In my case, there will be
Can
two
you come back
inputs.
to this picture and show so what will be the expectation pretty much?
Yes. Hold on. Mm, So, in my case, we'll have two inputs, and in that case, we can see basically if the two, it's almost like the two waves interfere, and we can see a peak over here, a dip over here, and another peak over here. With two inputs, that is what we'll see. Um, with three inputs, uh, it'll be a bit different. Just a small peak there, big peak there, small peak there, and so on for more inputs. Um, but yeah, let's stop that. Oh,
So you expect superposition of a kind of two Gaussian curves, something like that, pretty much,
mm-hmm,
right? And
mm-hmm,
also, it's highly non-trivial. Actually, I know that one of my masters is Professor Adam Paszkiewicz, from which University of which is very much different than current Polish Minister of Education in his approach to students, but they work at the same institute. So anyway, Professor Paszkiewicz is specialist on the or this distributions, but it's not so trivial to prove Gaussian distribution to take place for various cases.
mm-hmm,
So it's of course it's a distribution that has only two non-zero statistical moments and zero otherwise. So, but we might expect some richer statistics at some point. So, but anyway, so
mm-hmm,
actually, I just figure it out. You can later study so-called statistical moment. What is a statistical moment? And make a evaluation how many statistical moments you have in your simulation. That's quite
mm-hmm.
interesting to follow. I will let you know later about some details associated with this.
Okay.
So this will be also an exercise, but also it's just curiosity to what extent it can be, how many moments will come out. Most
Mm-hmm,
likely two dominant, but could be even higher, which is not an ideal Gaussian uh, statistics. Okay, go ahead. Mhm.
right, all right. So a Galton board. Oh, um, so um, let's move on to the second slide. So as I've said before, we use two inputs and eight outputs for this particular Galton board implementation.
How many
Um,
layers in between do you have?
um, I forget, but I think it's four, was it?
Yeah, it's
I'm pretty
actually
sure it was
better.
four.
Yeah, it's better not to forget. Yeah, sure.
Yeah.
Yeah, yeah. Okay, go ahead. Mhm.
Um, okay. As we saw in the picture of the Galton board a couple of minutes ago, um, the grains of sand or the marbles striking the dots, they produce a random movement for the marbles or the grains of sand. And we can simulate that with Python code or C++, because we can
I
just
would
import.
not call it random
Mhm.
movement. I would say some level of stochasticity
Yeah.
during the reflection phase, right?
Hmm.
Because the
Hmm.
size of a grain is not fixed, and this surface of a grain is not always well predefined, and also this dynamics of a small reflection is also not fully, in a sense, graspable for determination. So, in that sense, it's random, but it's not exactly random move. But anyway,
Right, 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 of course. Yeah, let's say random looking. So that is something we can simulate with other other coding languages, but in VHDL, especially in FPGAs, it's going to be a lot harder because it doesn't really have a random function. Well, nothing is really random, as Professor Pomorsky explained, but at least we can simulate that with other codes. Not here. We're going to have to create something that seems random. Here, one of the ways we can do it is with a LFSR, which is a linear forward shift resistor. Um, and I would go into details of this, but it'll um,
actually, you
uh,
can go. It's even recommendable if you can go.
uh, I'm not prepared for that.
Okay,
It's
sure, sure. Okay,
yeah,
go ahead.
unfortunately. But yeah, it's a pretty simple concept. If you want, I can send you. Actually, I do owe Professor Pomorsky a video on LFSR or some resources on LFSR, which I'll send, which you can share. But so what we do with that is we just shift the resistors in a way that our outputs seem random. Um, yeah, one of the reasons we use LFSRs usually in FPGAs for random logic is it's it's because it's almost no logic. It just runs with the clock, and it's basically like a flip-flop or a D latch or a SR latch that basically runs with the clock, and the outputs seem random, but they are not really random. And it requires almost no logic, which means it requires less resources to create the random um, create the randomness. So let's move on. Um, so here, this is the LFSR module. The clock, as I mentioned before, the LFSR works with the clock. The reset is just a reset that we can use, especially in a process block. Oh, this is something I didn't explain. Okay, let's go through with this one. In a process block, what usually happens when we code it in VHDL is the process block is based on a clock and a reset signal. So what the reset does is when the reset is zero, the data basically goes to default. And the other stuff is based either on the rising edge, which is the first um, the part where the clock reaches one first, or the falling edge, which is the other way when the clock first reaches zero, or yeah, um, when it is falling. Um, and the random bit, it uh, is basically an output of the least significant bit that we're going to use for other modules. And yeah, so this is what we'll use for the randomness in other modules that we'll see. And it's basically yes or no for the left or the right branching after it hits the dot. on the or after it hits the node on the Galton board. Now the state is something that I will need to explain a little bit. So, how I imagined this with a Galton board is basically like a binary tree. So, in a binary tree, when you have like uh, in a balanced binary search tree, let's say to be accurate, when you have when you have eight leaf nodes, that's the floor of n by 2, which means you'll need to have 16 to go all the way to the top, right? So that is what I thought of because we have two inputs and then eight outputs. So we'll need 16 on each side to make it basically uh, viable, I guess. So the state here, that is why it is 15 down to 0, which basically means like in an array, when you code in any language in an array, when it starts with 0, it's the elements start from A0, A1, all the way to A15, which is 16 elements. So that is why it's 15 down to 0. And yeah, that is how you make arrays in VHDL. You define them as standard logic vectors and then add a size for them. So let's go through the process block. So the process block, as I said before, it is based on a clock and a reset signal. When it is 0, just a non-zero, just a default value for R. And this one is based on the rising edge. And when it's on a rising edge, just take a just take the XOR of the last gate on the last what we call the last nodes before the leaves, and R is everything except for the last bit, bitwise ANDed with the feedback. Oh, and yeah, so that is basically the LFSR for 16 bits, and this is pretty standard logic for LFSRs in VHDL. Let's go to the next slide. Now this is the Galton core, and the number of stages for each of the for each of the particle is we have at least 7 coin flips, and this is the counter is just a limit that I've placed on the bits that we can have in a particular bin, the last 8 bins. That's just a limit I've put on it. So that would mean we have about 2 to the power 16 bits in that bit counter. So as the counter gets to 65,000, it resets. Yeah, 65,000, it resets. And the step div, I added that because I originally the board clock, the fabric clock on this board, it goes up to 100 megahertz. And I previously coded on it, but I couldn't see any results because all of the LEDs were constantly on, and I did not know what was happening. After some research, I figured out that it was because the clock was too fast for me to actually see what was going on. And yeah, I basically added a variable to make it so that we only have 1K events per second instead of per megahertz. Yeah, so and this is basically the same thing that we did before. The clock, the reset, run, and the LEDs for the um, and the LEDs for the outputs. Um, what else? Oh, the bin flat. Oh, my bad. The bins flat. The bin counters. They're concatenated into one with this. Into just one big vector, and this is just for the UART top level logic that we use to get the data from the FPGA to the Python code that I did to represent the histograms that we'll see in a little bit. On the Galton core, as I've said previously, if you want to take the go from one module to the other that is not the top module, we need signals. So that is why I've defined the LFSR signals on the Galton core. And this is where what I did previously added the step division, it comes in here as a clock. So we slow count that and turn it into a slower clock using something that's called a PLL, phase lock loop. And what that does is it allows me to divide the natural fabric clock of the FPGA and basically have a slower clock. And these things, the bin counts, those are like basically counting how many events was detected in that particular leaf. The LEDs, of course, for the output, it's connected to the bin. Yeah. Okay. Now the pop count, uh, it is this is a important concept that we have done for this project. So what this does is it basically takes the pop counts, or like the counts for the 7 random bits that we had, and it gives out a 3-bit number that can have a impact on like the probability of where the um, particle goes, like half the probability to go that down, like down that way or down that way. Yeah, it's a 50-50 coupler decision, go this way or that way. Yeah, after 7 of these decisions, which we previously stated before, the number of right turns or left turns determine which of the 8 outputs gets hit. And this is basically the mathematical core of the logic that we have. And this basically, if you look at it, it kind of looks like a binomial distribution. It directly implements a binomial distribution, and that's pretty much what it is. Let's go to the next slide. This is basically us doing connecting the LFSR to the top module with a port map. And yeah, that's pretty much how that works. And this is a process block that basically does what we previously said. When the reset is 0, it stops the clock and the steps. When if it's on a rising edge, then if it's on a rising edge and the reset is not 1, and then what it does is it slow counts the normal count that we have. That process block is what implements the PLL, the phase lock loop in our code. Okay. And the next one. Okay. Now this is the process block that basically we use for the final logic in our code. So what this part is doing, the reset part is doing, is if the reset is 0 or on in this case. I know it's kind of counterintuitive because it usually means the other way around. 1 is 1, 1 is on, and 0 is off. But yeah, 0 is on this one. If the reset is blah blah blah, then bin count is bin counts last bin LEDs that are all reset. If not, then implement LFSR, the pop count, and then the bin count. Take that data and put it on the LEDs. That's basically it. That's basically all of the logic and the Galton board. Now we have something for the UART logic. It's not on the slides. We're gonna have to look at that in the files. But before that, this is the Python code that was done. What this does is basically it reads the data from the serial port. This is the baud rate, which is basically the bits per second for UART logic, but it's kind of not really correct to call it bits per second, but it's just the speed. This is something we corrected last time because I thought the results were supposed to be something else than what they were, and I tried to correct it, but apparently I was wrong to think that the results was wrong. The results were wrong. And this part basically plots it. The import part, we've seen this, right? The matplotlib, that's used for plotting stuff, serial and structure. Those are just basic Python libraries for serial ports and structures, like zip and stuff. Yeah, and so we read all the code, all the data, and if the data does not exceed, this is just for like overflow, a little overflow checking. If it doesn't exceed 16, then continue. This is us decoding the data, and this is plotting the data. Yeah, so let's just close that. I want to get into the FPGA part. And before we move on to the code, any questions so far?
Yeah, Eric, any questions? How much is to buy the cheapest FPGA? How much did you pay, and which web page is good for it? So to reproduce the case you are showing, can you show us the web page on which I can purchase such thing?
Yeah, sure. So I usually, for students, it's usually great to go to Diligent. So let me just share this web page right here. Okay. Diligent Corporation. Okay. Oh, or maybe I've misspelled it. Hold on. Yeah, it's Digilant. Um, so they have a lot of products here. So the one I have is the uh, Nexus Nexus Artix A7. This is the standard board used for students at UNM, but yeah, we can
Which one?
go with
Yeah,
this
the
one.
left, the Nexus. I see.
Yeah, the middle one.
What
Uh,
what's the typical price of this unit for with everything the set
yeah,
to
let's see. Yeah, it's $349.
350? Yeah.
Yeah, it's plus tax and shipping, which shipping actually takes a bit because they are manufactured in Taiwan and it takes a couple weeks to come to the to anywhere, I guess.
Yeah, I
Uh,
see. Only in Taiwan, I see. Mhm.
yeah, so yeah, but we can that's just for practice for students and stuff. But next or Digiland, they have other FPGAs like this guy that are a bit more capable, uh, and this guy as well. I've used a couple of these, but yeah, they make pretty good equipment. Now, uh, let's stop that. Let's go to code. All right. So, as I said before, so the random number generation that was done by the LFSR, uh, the actual core logic, it's in the Galton core, and yeah, the math and everything else, it's in the Galton core. And this guy, it basically connects all of these with the uh, board maps that we've created here. And this part is just the UART stuff. So what it's basically doing is if it's checking to see if the UART is busy or not for until that part. And it's indexing the bytes and it's putting the data in particular bins as we've defined it. And it's sending all of that through a port in our device. So it basically goes in this particular FPGA. If you see right here, I don't know if that's clear. The power port and the UART communication port, they are the same. So it may be that in some other FPGAs that you may want to try in the future, that may not be the case. In that case, you'll need another wire or another port to connect them. But in this one, we just have this guy. Let's just open the hardware manager. All right. Oh, let's connect to the port. And let's do that first. Okay. Let's code this to the board. All right. And let's put this. So actually, I don't know if you you guys can see. Can you see the Python histogram?
I only can see the code. No, I can
Okay.
see the graph.
All right. Okay. How about now?
It's confirmed. We can see.
Okay. All right. So let me let this go. And we can see on the board the data going here and there, but this is kind of too fast for us to really see what is happening. But with UART, we can really see that we have two peaks here and here, and it's basically a curve like that. And that is what we expect with two sources.
But
So,
actually, a question. So
mhm,
here, let's say you put grains from two sides.
mhm.
Do you allow grains to reflect? They can collide. That
Oh
would
no, no.
simplify. But I mean, just consider this process of collision. It's like
Yeah,
I mean,
I've
this would slightly modify results. Yeah,
okay.
but I mean, yeah, it's just and
Yeah,
also yeah.
I've not considered that part at all.
Well, in a
Yeah,
sense, scientific cathedra is like
yeah,
religious cathedra is a place for contemplation. So
yeah. That's
it's the
interesting.
way to place it properly. Yeah, yeah. So I mean, just think on in some perspective, right?
Hmm.
Sounds good.
All right. So now that
What
we've
is the
completed.
statistics of event how you have? So you need to go to the law of big numbers because there is essential what is the difference between probability and frequency? Well, the thing is that if number of events tends to infinity, the frequency of occurrence is almost the same as probability, right? Frequency of occurrence over total number of cases is a
Hmm.
probability in the limit of n going to infinity.
Hmm.
So probability is more abstract concept than just frequency of occurrence, right?
Hmm.
That's how it is. All right.
Yeah. All right. At the last, after this demonstration, any questions?
David, are you still on? Eric, David and Eric, any questions?
No, I don't have any questions.
So
All
I
right.
believe this methodology would be very nice because whenever you have superconducting electronics, you need FPGAs if you want to really control it on massive scale. So actually, what is was very surprising for me to discover is that like making Josephson junctions is relatively easy. I mean, it's not easy, but it's relatively easy. It's relatively straightforward. Actually, controlling many qubits at the same time requires very high skills for FPGA electronics. So actually, you cannot omit FPGA electronics in general. So that's how it is. So this is very vital part of a system. And so far, most quantum computers, is it ion trap based? Is it Josephson trap junction based? Is it semiconductor quantum dot based? They use FPGA electronics. The,
Hmm.
the key feature is that, for example, if a lifetime of superconducting transmon qubit, let's say, is 300 microseconds. So if you see some signatures of change in the range of during 2 microseconds, you can use FPGA to make a corrections. So but it has to be like response time 2 microseconds or something like that, or even nanoseconds. So this requires very high clocks from FPGAs. It's costly, and controlling units, FPGA controlling units. Uh, so FPGA based electronics that is serving um, uh, qubit control is usually very expensive. So products start to range from 100 kilo euro, 100,000 euro to, let's say, sometimes 500,000. And also, we recently revised the mock equipment by Liquid Instruments. So it's not necessarily, so it's about 50K basically per set. So that's a very, I think FPGA programming is growing skill, and it cannot be fully automatized. And so let's say there will be probably less need for Python coders and more need for FPGA programmers. So we are addressing very good topic for electrical engineers, for physicists. I mean, experimental physicists can never escape from electronics. So without good knowledge of electronics, he will never know what is, he will never conduct deep experiments. So that's how it is. Right. So anything more to add, Raman?
No, unless there's no questions, I think I'm good. I mean,
Yeah, it was quite a lengthy lecture, but it's good to have it. It's almost 2 hours, so it's like
oh, okay.
something like 1 hour, 40 minutes. No, that's very good. That's very good. So we like intense lectures. I always hate this so-called 15 minutes presentation, 2 minutes of discussion on overcomplicated problems. We never touch things in deepness. There's even no space for criticism or more fundamental questions. And usually it's let us thank the speaker again and we move on. So in a sense, this deeper style is really needed. All right,
All
guys.
right.
So let me finish. I will ask, let me finish now.